there's really a couple of domains involved here. Everybody's aware of this. But what we as yet don't have is sort of a unified mathematics of both the logical and the physical, or cyber and physical, if you will. And what I'm about to tell you about is an effort to provide two things, two solutions. And it's been deployed in the Navy for systems that are currently shipborne. They had a number of accidents over the last couple of years, sort of military ships hitting commercial ships. There was damage, there was loss of life and injuries. But the commander in this situation, or the lead for this operation, is currently much of the time focused on what you might call mission capability. So if you were looking at an arbitrary CPS, this would be the basic functions it was designed to do. And the CPS framework that I'll relate this work to provides a spectrum for partitioning or for bucketing the requirements for that system, monitoring. And then the reasoning engine I'll talk about as a possible way of drawing conclusions about both the logical and physical is being used to not only give status relative to those key concerns, but then also to give recovery strategies. So this slide is intended to simply convey the basic contrast here, that logic and physics really are those two domains you saw in that logo. And on the IoT side, which has become a much more pronounceable name for this area, is largely connected to value that can be derived from data streams. The CPS Public Working Group created originally this framework. It was published in 2017. It was about 500 people from industry, government, and academia. At that time, I was with what then was called Fiat Chrysler and was Daimler Chrysler when I joined them. So I was the chief scientist for electrical engineering. I'd like to say that this framework provides a couple of things, brings to the table to this systems engineering environment. It brings, one, a different functional decomposition, which basically has at a logical step of development, makes a decision about whether a function is going to be implemented logically or physically. This then determines the science and the methodology. Good example, late 50s, Mercedes had power door locks on that car, but they were actuated pneumatically. They were not done with signals, data on a communication bus, and an electric actuator, as in current models. So the decision at that time was to do this feature of function logically later on, but originally it was physical. This particular diagram is a small portion of that framework. It uses the notion, or refers to, trustworthiness, which is a composition, as you can see, of 5 different areas here. I've elaborated some of them in areas that people might be familiar, certainly the security piece in physical and cyber, and then the privacy piece. And the basic idea is that this is a process applied to an element of that functional decomposition, and the output of this operator is requirements related to that. So I've called out some of them there. Torque requests are part of certainly the robotics that we look at, but also, of course, automobiles. There are 3 types of torque requests, both steering, braking, and propulsion. And that requirement is called out there. On the encryption concern, a particular type of encryption is called out. And any one of these requirements serve as a baseline for function. The requirements could be elaborated in actual formulas, and those formulas would be relationships that constrain an unknown, much as we would in a differential equation, and then we use those relationships to derive computational content that ultimately can form the basis for control theory. So this work began with trying to take this framework and put it in a computational environment. In this case, it began with a UML. This is one small fragment which reflects some of those concerns. And this is all available, all of the code for both this open source piece, which I'll show you the purpose of, is contained in GitHub, and you're welcome to take a look at the code, to take a look at what was developed. So let me explain what it does. This trustworthiness piece, by the way, is the object of conversations that I've begun with European nations, both Sweden and France. And it's primarily because they're trying to develop what you might call a 5-star rating for artificial intelligence. In their case, it'll be a 5-star for cybersecurity. But the real problem is to see how these things can be quantified and how you can compute them. So it won't be 5-star in the trivial sense of many of the ratings we use for automobiles. The modeling effort took 3 different directions. I've called them out here. When this began, my aim was to provide a reasoning environment about cyber-physical systems that would, again, assess mission competence, and secondly, where there's failure, would give a recovery strategy. The OWL environment was not familiar to me in the beginning. They referred to them as ontologies, and my only experience with that was in Aristotle. But I did learn what they were talking about and focused on the code, actually, for developing that. The other is the UML, which largely reflects, through its associations, the mathematical model. And then finally, the XSD is an environment where you can, of course, develop a XML schema, or a type theory, if you will, of those functions. But you can also use XSD in the form of xquery, which has been shown to have the full power of a Turing machine, or full power of computation. So let me go and keep the time down so that we can fit our schedule. These are the dashboards that are currently being implemented for destroyer class ship. In that case, the power system is what we wanted to assess. And as you can see here, the CPS could be a system of systems. The dimensions of those concerns are about 110 of them, that each is associated with certain practice. In some cases, that practice has evolved into standards and therefore test cases. In other cases, it's a complete blank at this point. But the dashboard then approaches or addresses various levels of command. And the underlying assumption here is that no matter whether you're in a defense stature or you're actually worried about an autonomous vehicle, which was my hat many years ago, the levels of this organization are going to want dashboards. The requirements that I listed were not resolved into formulas, but if they were, you would find unknowns, and you would also find parameter values that are being measured in real time. So give the person that's making a decision a status, and if there is failure, let them understand the risk and take that risk if the mission is critical. So the competence questions, as the military refers to them, are really about mission capability or functional capability. But the example that I'll give you has to do with the ability to exercise a mission that involves sort of targeting TOH, or targeting over the horizon. You're trying to essentially hit a target you can't see. You're relying on a lot of off-board signals. And if there is compromised security, for example, then you can still make a decision to move forward with this action. On the automobile, if you look at the park sense sensors that are in the fascia, the rear and the front fascia of a vehicle, if you manage to bump one of them, knock it out of the fascia, the system will return a message stating that park sense is unavailable. So if you were actually to inspect the dimensions, the full range of that field of those sensors, you would find that 1 out of 6 or 1 out of 5 doesn't really disable the system, and the response should now be a little bit more measured. Perhaps it should say the driver should watch their left-hand door mirror in the process of using park sense, rather than disabling the entire system. So the lesson to be learned here relative to physical IT work or IT systems is that relative to security, really, there's better security through the physics because the mitigation surface is also much larger and includes both the analog and the physical rather than simply the digital. This logo or this statement in quotes, if anyone was alive during the Vietnam War, they will see the similarity to an old quote that said, "Better living through chemistry." So, relative to this framework, reasoning is now taking a position. We have implemented this, and it's intended to allow you to assess the dependencies between two quantities that, in this case, are not quantities in a quantitative sense. If it were quantitative and if it were a continuous domain, you would talk about the derivative of security with respect to safety. Since we don't have access to that type of calculus thinking, instead we moved into this reasoning space. And the purpose is to, one, various levels of language, also to expand or convert metadata into function calls that are related to abstractions. So I would say this is purely a case that could be implemented as a toolbox in the MATLAB environment, and what it would give both designers and, as I noted just a moment ago, dashboards to those cyber-physical systems. And I'll give you the flavor of this. This ontology is a formalization, of course. The vocabulary was a little bit unfamiliar to a mathematician like myself, but classes, objects, individuals, relations, attributes. So those are sort of classical mathematical terms. I think in the ontology community they talk about relations as properties. So that confuses the issue for someone like myself. But in this case, you see an example of what they would build for a conceptual mapping. Use case, this is LKS, so this is lane keeping assist. So for those not familiar with these automotive acronyms, lane keeping warning would be something that simply in your cluster would give you a chime, it would give you a light, it would tell you that you're leaving the lane. It might even have a graphic that represents the extent to which you've left the lane. In the case of assist, when that's added to these automotive features or to aerospace features, this indicates that there's a possibility of actuation. What I've included here is not only the model for a use case which has to do with public safety or body cam, as well as the automotive one. And you can see that in the body cam case, they are very primitive. The 5 that are already deployed don't have broadcast to off-board command center. They simply have onboard recording. And I've given you a simple way of using colors and graphs to capture that cyber-physical system. The dotted lines indicate logical connections. The physical lines are influences or forces governed by differential equations. So the formalization, I won't run you through all of what's going on, but effectively you're trying to build levels of language. At one level, which the ontology community refers to as axioms, and the mathematical community would refer to as rules. Rules are very easy to track with a constructive approach, with rewrite rules are the basis for computation and compiler construction. The idea is to simply capture those best practices and insights into the relationship between the constructors and then influence the overall performance and be able to compute it using. And 5 minutes over, okay. So I will leave you to look at these later, exactly as how this is done. And the reasoning tasks or ask a question is trustworthiness satisfied. This is now computation because it's related to the status of the requirements that were added for trustworthiness. Is encryption of memory required to satisfy that trustworthiness? So the system, the onboard system for the Navy would give you a failure of cybersecurity on the confidentiality level, or it would tell you that the camera and the body cam is dropping frames and therefore there's a failure of a functional requirement. What it would recommend, if it's a multimodal cyber-physical system, is a reconfiguration so that you can recover trustworthiness.